Hello, good evening, everyone. Sorry I get late by 2 minutes. Today we are going to discuss about tree and graph. I gave you some practice problem too, so let me know if you have done it or not. If you have done it, just let me know the approach too. I guess there were two linked list problems. The first way to detect the cycle, and second way to reverse the linked list. Both were the very classical problem. Let's wait for a few more minutes before we move on. Yeah, good. Detecting cycle is pretty easy, and both problems were actually very easy. Second problem is to reverse the linked list. That solves very easy, but like the implementation is a bit confusing, but overall it's easy only. Okay, let me present. Okay, no problem. If PPT wasn't there, I will explain you the question. Question is like first question is you have to detect the cycle in the linked list. The second question is to you have to reverse the linked list. You are given linked list in both the cases. And one more problem was there that you have to find element in in a sorted array, which we had done yesterday. So let's start. We can start. Okay, let's start. So let me explain you the problem. I told you problem is very simple. Like you are given linked list. The linked list you are given this linked list, and you there might be a cycle in this linked list. So you have to figure it out whether there is a cycle in this link. In this case, there isn't any cycle. This is ending to null, right? But some case be there like this. this, and this is like pointing to this node. Okay, so there is a cycle, like, right? So you have to detect if there is a cycle in this linked list or not. So what we can do, one approach we can do is, like, we can have two pointers. The first pointer will be named as slow pointer. This is very basic and pretty straightforward. I like a must done problem. If you have done linked list before, you must have done this problem. Okay, so now this will be the fast pointer. As the name suggests, slow, it means that it will move slowly and it will move fastly. So what does it mean? It will like leave one element. So it will bounce. It will at each step it will take two steps. So like at first slow and faster at this place. In next step slow will go at this place. It will take one movement, but fast will take two movement at a time. Like it will go here and here in the first step, like it will jump, that kind of thing. So fast will be here in the first step. In the next step, s will jump from here to here, so s will be here. Okay, and in the next step, fast will jump from this, it will jump this next one, and it will move to this one. Fast will be here in the next step. Fast is not here, fast is here. In the next step, s will jump one more, s will be here, and fast will, like, from this place the next pointer is like in this direction. So fast will move in this direction, it will jump this one, and it will like here. So if there will be any cycle, then this condition is going to be true, that s and f will be at the same node after such iteration, because this is moving fastly and this is one is moving slowly. The fast one after taking a circle, it will come back and it will match with this slow pointer. So this is our approach in this. But in this case, if there isn't any cycle, fast will keep moving this. It will never come back to take to meet s. If there will be a cycle, then only this case will be true. I hope you have understood this. No, it's not a circular linked list. Circular linked list, in that the first element, like, it should be circular list. It should be like the last element is pointing to the first element. In cycle, it is not necessary. It could be like this element is pointing to this one, the last second one. It could be anything. It could be pointing to the first one to this one too. So it's like, I hope you understood. Yeah, so let's code it. We will be doing it in the here only. So what we have done so far, like, we defined two pointer in this. It's defined the node name of the node is list node. List node is each node. Okay, so this is the data type of linked list node. So we'll be doing this like fast is equal to head. See, head is nothing. Head is like this one, the starting pointer. Like, the function is giving you the pointer head pointing to the first variable, this one. Okay, so let's code it. List node star slow will also initially point to the head. Then we will do this until we exit the condition, and condition will be like if fast is not equal to null, or fast dot next. I will explain you this way. So what is this condition? This means that the fast pointer will move fastly, right? As the name suggests, it will move fastly. It will go here, it will go here, and then a point will be there, then this will become null, right? If there isn't any cycle, then after some time it will become null. The fast will become null first. So that's why we aren't adding any condition on this slow pointer. Just to avoid this condition, when this is not null, we are writing the condition. And if this there is any cycle, if there is any cycle, then this condition null condition is not going to true, because you know, right, there won't be any null. It will be like keeping moving in this circle again and again, again and again, right? So it says for reversal increase this problem. Okay, so in this now, let move slow is equal to slow dot next, and fast will be skipping one node. So fast will be fast dot next. The next is used to go to the next element. Yeah. So fast is equal to fast dot next will be the next element, the next of the next element. So it's like we are skipping one element in the net. And after this, we will check if fast is equal to slow. If this condition, if there is any this kind of condition is not, if there is any this kind of condition, then it means that uh, there is any cycle. Okay, so let's make a variable bool answer, which will initially be false, which note that there is any cycle. But if this condition is true, means that there is any cycle, then let's make answer is equal to true, and we got a cycle. Let's break the loop. We break it, and in the end, we will be returning. We have to return boolean. Like if there is any cycle, then we have to return yes. So return the answer here. Return answer. Let's see if it works. Hope it should work. Hope is pretty simple. Now it is giving error. What kind of error is this? Sorry, it should be, and both conditions would be true, right? Yeah, it is passing. So, let's see, both conditions should be true, right? If any of these fails, we can't move forward. Yeah, I hope you understood. This is a pretty simple. I hope you understood. Let me know quickly. No, there isn't any other approach. You can go with map or something. You can go with map, but this is the best approach in this. It's a linear approach, first thing. The second is that you aren't taking any space. But when you will go with map, the complexity will be in login, and because in map searching, if you assume the searching take off one time using unordered set, then still the time complexity will be linear, but the space complexity of OFN in this there isn't the space complexity like the time complexity for this. This is a optimal approach. Like in the interview, in this there can't be any optimal approach than this. Space complexity, time complexity will be O of n, and space complexity is if O of 1. You can go with map set 2, but that is like you are unnecessary using some data structure, but that definitely you can solve it using that. But in the interview, like if you solve using those data structure, the interviewer might follow you to optimize it, and this is a optimized solution. So let's move to the second question. The second question is like you are given a linked list and you have to reverse this linked list. and end is pointing to null. Okay, you have the linked list. Suppose this node 1, 2, 3, 4, and this 5. Okay, so this is the input. This is input, and the output should be like this. Output should be the reverse, like this one should be pointing to null, and this 2 should be pointing to 1, this 3 should be pointing to 2, like just we are reversing it, and 5, yes, like this. So do you have any idea how you can solve this problem? This is a pretty simple problem. Like, but the approach is a bit confusing, but it's a simple tool, very simple. Let me know if anybody of you have done this problem before. I'm sure, like if you have studied linked list, you must have done this. So let's move. I'll explain you how to do this. This is a linked list you are given. Okay. Yeah. Okay. No problem. I will explain. This is a linked list you are given. Initially, the you will have a variable current that will be pointing to this current number. Okay. Then what you have to do? You have to point this. The next of this should point to this direction, like left. Okay, point to null. So let's make it something like a previous node. There isn't any node. I'm just assuming there is some node. So let make a pointer, previous pointer. Let make it like previous node or something. Previous node. This is a pointer pointing to null. This will initially be pointing to null. Okay. So what should and we will making another pointer pointing to the next of current, like this one. So what my approach is, like why there's a need of such pointer. See, when I make next of current to this null, i will lose the I will lose this information. I won't have any idea of this, because the only way to get at node 2, this node, is by current dot next. But if I make current dot next is equal to null in the first stage, then I can never reach this node. So I need to save this node too. So I will be saving this node by next node, by using a variable next node that will be pointing to this place. So what I can do is, now I can do one thing is next node is equal to current dot next. Okay, I guess you have understood the logic why we are using three pointer here. Current dot next. Okay, then current. Then we will make current dot next is equal to previous. Why? Because now this is previous node is right now null. So current dot next is equal to previous. Now we lost the control of this using current. So that's why we stored the into the next node. So current dot next right now is previous node. So up to now the condition is like we remove this and we make a path to the left. So it's like we remove this and we make a path to the left. This is pointing to null. Now Now this is done. Now what we will do, we will make previous node, this previous node will now be this current, and we will make current equal to this. We will shift it one to the right, like current will be 2, previous will be 1, and next node will be 3. That's what we want. So current, so previous node, so previous node, so previous node is equal to current, this current, and current is equal to next node. Next node, what was our next node? This was our next node, right? So now we are making current will point to this, previous will point to this, and next node will point to at this place. Okay, so current is equal to next node. This is what we have to do for each and every node that we have to reverse, right? So how many nodes will be there? So we need to run this we have to do this for all the nodes. So we can use a while loop. While loop, if current is not equal to null, current is the right element under observation. If this is not equal to null, we will be keep moving, because in the end when it reaches to this place, this null element, we don't need to do anything, right? Because we're done. So this for loop will, this while loop will get cancelled immediately. So this is the code. Let's code it. I hope you have understood that. I explained it in a good way too even. So let's see if we can solve this. In this we have 3 points, right? So let's make list node star previous node is equal to null. Initializing it to null. Okay. List node star current is equal to head. Head is nothing but the first pointer which is given to us in the function. Okay. Then list node star is equal to next node. Next node is let it be null to initial. Okay. Then we will be writing a while loop while current is not equal to null. If this is true, then what we can do? We have to write this, right? We have to write next node is equal to current dot next. Let's write it. Always try to write the pseudocode in your notebook or page at first, so that visualization will be easy. Current dot next, and current dot next is current dot next is equal to previous node. Previous node will be equal to current. I guess I'm writing current. See, current dot next is equal to previous node. Previous node is equal to current, and current is equal to next node. Yeah. There is a kind of pattern you can see, like when we are assigning some variable to some number, in the next null we are assigning the value to it. Like current now there is a diagonal kind of relationship. You can say current dot next is coming here, current dot next, previous node from right hand side, in the next hand it's coming to the left hand side, from this current is coming from this place to this place. You can see pattern, or diagonal shifting you can say. And in the end, what will happen in the end when you in the end the current will be at this place, right, when the loop exit, and at that point the next node will be somewhere here only, because it will be always be to the right of it, and it will also point to that, but the previous will be pointing to this, but the previous will point to this, right? So we have to return this previous, because this will be our answer, this will be our head of the new linked list. So we have its return previous, and let's see, run it and let's see if it is mirror or not. It is mirror. Okay, okay. Problem is that it should be capital. It was defined here in capital. Here you can see in this node. N is capital. I'm writing in small. Okay, still it is giving error. List no. What's the problem? Okay, okay. Previous no. Just passing this three cases. Let's submit it and see if it passed or not. It's pretty simple. Yeah, it's passing. The solution is quite good too. It's like 1800%. So we are done with yesterday's session. And now let's move to the today's. Today we are going to discuss about graph and tree. So how many of you know or have you studied this before? Just let me know quickly. Yeah, cool. Okay, so let's start with some of you have studied this. Okay, no problem. So what is graph and tree? So graph has like a structure. Sorry for bad formatting. I will send you a good formatting or format to format it. Okay. So graph is a structure made up of nodes which is called vertices and that are connected by edges. Okay. So I will explain you here only. Okay. So graph is nothing like as you can imagine what a graph means. Graph is like there will be some nodes, there will be some nodes, and there will be edges. It's not like linked list. There will be and these are nodes. It will be like this. This is connected to this. It will be connected to this. It will be connected to this. It connected like these. These are all a graph. These are a graph. It's not necessary that all elements should be connected. It could be in a form of this. Or if we are saying it in hierarchical order, it will be like this. These are one of the most frequently asked questions in an online company's assessment or placement or in the interview program. Okay, so this. So graph is like that, or I think we have understood what a graph is, and these are called vertices. These are called vertices. Wait. So these are called vertices, and these are edges. These are edges. And the difference between graph and tree. The tree is nothing. It's a graph too, but there isn't any cycle. There might be some cycle. This is a graph, right? There can be some cycle in this graph. Like this is a cycle. You can go from this position to this. Like this is a cycle. Huh? You can go from this position to this position from there. So this is a cycle. But a tree, fruit tree, A tree is a special case of graph in which there isn't any cycle and there exists only unique path between two nodes. So what does it mean by unique path? So if we select these two, like this node and this node, we can go from this node to this node by this path, like by this path. Yeah, by this path. We can go to this node by this path too, like going here, going up and now like this. We can go at this place by using this path too, like at first we'll go here and then we can go at this position. Like there are many paths to reach from this node to this node, okay? But in the tree, this is tree. How we can say this is tree? There isn't any cycle. There isn't any cycle forming in this. So this is a way of a graph. This is a graph only, but with the condition that there isn't any cycle in this, and for each and any node, like choose any two node. For the timing, let's see this node and this node. There is only one way, one path to reach from this node to this node, that is through this, right? Let's see for this node, like for this one, and even for this node too. Like there is only one path, right? And that is like we can go from here to this. Like this is what. I hope you understood this. Yeah. So this is what a tree. A tree is a special type of graph that is connected and has no cycle. One more thing that I forget to tell you, that it should be connected. What is meant by connected? See, this is a graph tool like this. This is a graph like this is a graph tool. This all together, this element, this all are a graph. Because graph need not to be connected, but these are not connected. You can see these are like separate entity, right? They don't need to be connected. But for a tree, it should be connected. For calling this graph to be tree, it should be connected means that number of connected component which we can in graph we have a term which is used to count how many connected components we have. In this case, it's two. Like this is first and this is second. You can say the number of connected component in this. You can just tell me quickly how many number of connected component in this. Like this, this. Like just tell me if you have understood how many number of connected component in this. In this too. No, I'm not saying. For a graph to being a tree, there need to be many conditions. The first is that there should be only one way to reach from one node to any other node. Okay, there shouldn't either to this node here. There is a many way to reach from this node to this node. But if it is a tree, this is a tree. There will be only one way. Choose any two node, and there will be only one way to reach from one node to other node. Are you saying that six connected component? Just understood now. See, these are connected. This is connected. This is one connected component. This is one connected component. So this is the first connected component. This is second connected component. Like each node is itself a graph too. This is a single node graph. This is one connected component. So how many connected component is there? Three, total three, right? Yeah, there's a problem link that, like, I don't know if there is a problem on internet or not, but like it's a very important question to differentiate. Like anyone can ask you if you are a programmer. In these two, there is three. This is the first. You can do it too, write it on your own. Like if there is no cycle and the number of connected component is one, then I think you're good to go. You could get through one. This is two. This is the total three connected components we have. Like this is a itself a connected component and itself a connected component. So total number of connected component is three. Okay. I hope you understood it. One node is a root. The root will be given to any node can be a root. Okay, every node connected by exactly one path. This is what I have told you. And each node have zero or more children, but only one parent. Yeah, one thing I forgot to tell you uh, in this figure, you can see that for each node there is only one parent. For this node, whatever we have below this is a child of this node, right? This is a child. Whatever from where it is coming, this will be like its ancestor. This will be the parent of this node. This node will be the parent. Okay. So in tree, each node will have only unique parent. It will be coming from a unique parent. But in graph, we can say it like this node is coming from this place. This node is coming from this place. So there isn't any unique parent, right? If you are saying a tree, you should define the root. Any element could be the root, right? But if you are saying tree, you need to give the root. Okay. So let's see, you are given a graph. Now you need to traverse the graph. For traversal, there are two kind of traversal. The first one is the DFS, which is called depth. Sorry, the first is here we are discussing is BFS, then we will discussing DFS. The BFS stand for breadth first search. It is a method, or it's just a method to visit the all tree. Yeah, this is also a condition. Like if you have to detect if it is number of edges max n minus one. Yeah. But with this condition, like for proving a graph to be a tree, the sufficient condition is that if the number of edges is n minus one and connected component is one, both conditions should be true. You can't just go with if there is n minus one edges, you can't guarantee that it will be a tree. If the connected component will be two, then that condition is satisfied too. Can be satisfied, but it won't be a tree. Okay, so just make sure to apply both the condition. And BFS explore the nearest node first, level by level. See, BFS is also called level order traversal. So I will explain you what a BFS is. Okay, so let's go. So this is suppose we are dealing with tree. Okay, so this is a node. This is a root. We are given this is a root. Okay, this is a root. This is a node. Let the name of this root be one, two, three, four, five, six, seven. Okay. So in the BFS, it's called level order traversal. This is level one. This is level zero. You can say L0. This is level 1. The distance from this route is 1. This you can say h is equal to 1 distance. So this is at in distance 1. This is at distance 1. So at first 1 will be traversed. Then 2 and 3 will be traversed because it is at distance 1 from the route. Then at distance 2, what is at distance 2? This is at first 1 distance, 1 distance. 4 is at distance 2 from 1. 5 is at also at distance 2 from 1. So 4, all like 6, 7 is also at distance 2. So all will be visited now. 4. So these all will be visited. This is what DFS is. Sorry, I'm confusing. It is a BFS. This is BFS. BFS stands for breadth first search, and this is also called level order traversal because we are traversing level by level. This is level 1, level 0, then we are traversing level 1, then we are traversing level 2. Okay, this is level order traversal. And what a DFS is? DFS is like depth first search. We are going on a depth. So it's like this is a node. This is a bit difficult from BFS, but it's easy to. You can't. It's not that difficult that you can't understand. Okay, so approaching this problem, we will like suppose this tree is given to you with node with a same value like 1, 2, 6, 7. Okay, so in this this is again the root. We will be starting from root. We'll be starting from root. From root, we will see how many children we have. At root, we will check its children. There are 2 children. This we were traversing. We are at root right now. Suppose we traverse what? Now, we will go to its children. We will see, does it have any children? Yes, it has a children. We will go to its children. Let's go to 2. We can go to 5 too. Like, but for the time being, we are going to the 2. Now at 2, it means that we went at 2, so we traverse 2. We get traversed. 2 is traversed. Now we'll see, does 2 have any children? Yes, it has children. So move to its children. We now at 3. At this place, we can go to 4 2. Okay, like just we have to move to children. Now we are at 3. So 3 is traversed, right? Let's write 3 here. Okay, now that at 3 we will see, we'll check, does it have any children? No, it doesn't have any children. So we'll move back. We will move back to 2. Now at 2 we will see, does it have any other child which is unvisited? This child is visited. Yes, it has a child which is unvisited. So we'll move at this 4. Now we at 4. So 4 is visited, right? Now we will go back. Now at 4 we will see, sorry, 4 at 3, does it have any child? No, it doesn't have any child. So we will move back to this place. We'll move back to 2. And now we will see, does 2 have any other child which is unvisited? No. Like you have only 2 child, 3 and 4. There isn't any child which is yet to be visited. So we will again move back. Now at 1, we will check, does 1 have any child which is unvisited? Yes, it has. So we will move to this 5. Now we will write 5. We are traversing 5 for the first time, right? So right here. Now for 5, we will see, does it have any child? Yes, it has. So let's move to one of your children. We move to 6. Let's write 6 here. For 6, we will see, does it have any child? Does it have any child? So no, it doesn't have any child. So we will move back. Now for 5, we check, is there any child of this 5 which is unvisited? Yes, 7 unvisited. We will move to 7. Now we are done with 7. We are at 7 and now we will see, does 7 have any children? No, it doesn't have any children. So we will move back. Sorry, we will move back at 5. Now at 5, we will check, does 5 have any children which is unvisited? No, it have only 2 children, 6 and 7, and both are visited. So we will move back to 1. Now if we see at 1, does 1 have any other children which is unvisited? No, it has only two children, 2 and 5, and now both are wasted. So we are done. This will be the DFS traversal. Sorry, pen is not working properly. I hope you understood. Yeah, in this case, it is a pre-ordered tool, but it's not always necessary that it will be a pre-order. See, pre-order thing is like for binary tree. There could be possibility that this element, this has three children. Like there is one more node at this place, right? So you can't just go with pre-order thing. It's like in generalize. Any node can have any number of children. So pre-order post-order only works in a binary tree. Okay? So DFS can work in graph too. Like you don't need to be worried about anything. If there would be eight at after getting from seven, after getting at five from seven, we at five we'll be checking is there any other node which is unlisted? Yeah. So we'll move to eight. So here eight would be there in that case. Then after visiting it doesn't have any children, we will move back and then we will move back to one as we did before. So I hope this is clear. Okay, so now it's time to code it. So let's see the pseudocode of the first BFS. Okay, so let's move on with BFS code. In BFS, we will be using a queue. So what a queue means, so suppose why we are using a queue, we will see. So this is the graph. This is a tree you are given. Okay. Okay. This is a graph. So at first, this is the root. Root is given to you. Let it be the R only. Okay. This is the zeroth node. This is the first node here. In this time, we are starting indexing by 0. 0, 1, 2, 3, 4, 5, 6. Okay. So at first, we will be inserting a queue. Queue is this kind of a structure in which the element which is inserted first will be removed first. So that it's like we are inserted one, two, three, then whichever element which were inserted first will be removed. It's just like a normal queue you have seen in the bank or something. The person who came first will be getting its document or whatever work he has, its work will be done first. So that's what exactly queue is. So at first we will be inserting 0 in this queue. Okay. So now we will take this element 0 and we will see its child. How many child we will be inserting its child in this queue. So how many child it have? It have two child. So we add first we added this, then we remove this first element from this. Now 0 is removed from this. Okay, from this queue. We have 0 in our hand. And we will see the children of 0. What children? The 1 and 2. Let's insert the children in the queue. 1 and 2. Okay. Now it doesn't have any other children. Okay. So this will be traversal up to now 0, 1, 2, like 0 and then 1 and 2. This is getting like 0. We got 0. Let's add. It will be like this only. Let the 0 is traversed by us right now because it has been removed from the queue. Okay, just understand this. Okay, it get a bit confused here. Okay, confusion, but it's okay. Let's see. It will be clear. Okay, now 1 is removed. Now take the take the element from a queue. Now which the element will come first, like from the queue, the 1, because 0 is not there. 1 is the one which came first. So 1 will be removed. 1 is removed from the queue now. Okay, now Go to the children of 1. Does 1 have any children? Yes, it have any children. It had children 3 and 4. Insert 3 and 4 in the queue. Insert 3 and 4 in the queue. Okay. Now 1, we are done with 1. Write 1 here. Okay. Now, which is the element that will be removed from the queue? 2. Right? 2 has been removed now. 2 has been removed. And see, does 2 have any children? Yes, it have 2 children, 5 and 6. Insert 5 and 6 here. Okay, 5 and 6 here. Now 2 is done with. Now 2 doesn't have any children. We inserted all children of 2, so 2 will be here. Now which is this element? So now we will be taking this element 3 and 3. Let's see the children of 3. Let's see 3. For 3, does 3 have any children? No, it doesn't have any children. So just remove 3 from here. Okay. And add, since 3 doesn't have any children, so we don't need to add anything into the queue. Just make 3 here. Okay. Then again, go to 4. 4 also doesn't have any children. So 4 is removed from there and we don't need to insert anything into the queue. Then again with 5, 5 also doesn't have any children. We take out 5 from this and 5 doesn't have any children. So we don't need to insert anything instead of 5. And then take out 6, 6 doesn't have any children. So this is how the BFS traversal is using this queue data structure. Yeah. Okay, so let's code it in real time. So in this function, we will be writing a function BFS. In that, we will have a node. In the node, the current node, or let it be the root. You are given the root. You are given the vector in which you have to store the answer. Let it be data structure. Okay. And okay, I forgot to tell you one thing. How? See, these are the pictorial representation of graphs. How will we be representing it in code? So in code, suppose for this code, for this graph, this simple graph, for this graph, suppose this is 0, 1, 2. 0, 1, 2, there will be a matrix which is called adjacency matrix. There is a two-way to represent adjacency matrix and adjacency list. So matrix is like you will have 0, 1, 2. Since we have 4 nodes, 0, 1, 2, 3, 4. 4. And here also it will be like 4 cross 4. So it's like basically 5, right? Starting from 0, 0, 1, 2. I don't know, pen is not working properly, so just bear with it, okay? So 5. See, there are, so if this intersection, if this 0, 0 intersection, if there would be 1, there would be 1 only if there is a node from 0 to 0, like 0, 0. It's like from, sorry, it's like from, it's like 2, okay? You can take it like this. Is there any node? Is there any node from 0 to 0? No. So there will be 0. Is there any node? Is there any edge from 0 to 1? Like for this place, It's like 0, 1. Is there any edge from 0 to 1? Yes, it is there. So it's just like 1. Is there edge from 0 to 2? 0, 2. What was the position? 0, 2. Is there any edge from 0 to 2? Yes, there is. So it will be 1. Is there any edge from 0 to 3? No, there is not any edge. So it will be 0. Is there any edge from 0 to 4? Direct edge, not like indirectly edge. You can go 0 to 4. But is there any direct edge? No. So it's 0. So 5 is not there. Okay. Then again, 1, 0. Is there any node from 1 to 0? Yeah, there is direct edge. So 1, 0. Then 1, 2. No, there isn't any. So 1, 3, 1, 4. This here in this way, the adjacency list, all list will be completed. Sorry, adjacency matrix. Adjacency matrix. But in this case, it is like it is taking a lot of space. Okay. So what we can do, we can make a vector that is a adjacency list, and in that list for we can store only this element. For 0, we can store it as a list of how many elements which are directly connected to it. Like this, how many elements are there. So in the list, it will be 1, 2, only 1, 2. We don't need to store 0 or 1 for even elements that are not here. Okay. For 1, it will be a list containing element that is directly connected to 1, which is like 0, 3, 4, right? 0, 3, 4. Similarly, for 3, what are the element that is like for 2, what are the element that is directly connected? No. For 2, it will be only 0, because 0, 0 is the only one which is connected. Hope you have understood it. So let's go it. Okay. So vector, we are taking adjacency list QB, and now we will define a queue. This is how we define a queue. Queue will be inserting root, and yeah, we need to make a visited too. Like some node will be visited. We need to keep the record if the element is visited or not. So that's why we are making a visited. But initially, it will be 0. If some node is visited, we will be making it 1. So it marks that a particular node won't be visited twice. Okay. So now let while run do if queue is not empty. If we will be running slow, if queue is not empty, then if queue is not empty, let's take the current element. Current element top. Like we will be taking the removing the element from the queue using function queue.front. Yeah. Then remove the top element since we have used it, and mark this element visited. Visited current is equal to 1, and this element we have to also insert this element in our data structure. Post back current. Okay. Now let's check if this element has a children or not. For auto child in of this current. It is the adjacency list. It will see in this list does it have any element or not. If it has any element, it will be children. Okay. So if that children is unvisited, okay, if that children is visited of children is equal to 0. If that children is unvisited, it means that we need to visit it. So we will be inserting it into the queue dot push child. Okay. And that's it. We are done. I guess return it from here, and let's make the adjacency list. N. N is a number of element, number of node. So take, since it will be tree, so there will be n minus 1. If there is an n node, there will be n minus 1 cases. So we will be taking this much. First, we need to make our adjacency matrix. sorry, adjacency in list. 10 plus 1, yes, done. Okay, so we will be marking the edge. So A, B, C, X, Y. We are taking inserting element X and Y. X and Y mark that we will be taking input from the user. Okay, so it means that there is an edge from X to Y. Okay, so let's take input from the user as X and Y. Then yeah, it is in list X dot pushback. See, if there is an edge from X to Y, in the adjacency list of X, there should be Y, right? And vice versa too. In the adjacency list of Y, X should be there, right? So that's it. Let's call the BFS function. BFS function with which is the 0 being the this position, root, assuming 0 is the root, and what we have passed here, DS, AB, and visited. DS, AB, visited. This is what we have. And since we are passing BS, we need to declare DS2. DS is just a short form of data structure I'm using. Adjacency have been declared, and I need to make uh, visited 2, and it's initializing this value with 0. So let it work, and let's see how it is traversing. Code like going with the code might be a bit difficult right now, but like just for the beginners, like for them who are understanding it, learning it for the first time, this could be a bit quick, but just understood the logic, the pseudo logic that you have understood so far, that will help you see how things Intel. So okay, so let's give. So suppose there are 5 nodes, this and 0, 1, 2, 3, 4. So there is an edge from 0 to 1. There is an edge from 1 to 2. There is an edge from 1 to 3. You can see I'm making a simple graph. 1 to 4. So 5, so there will 4 condition, right? 0 to 1, sorry, 1 to not there, 0 to 2, 1 to 3, and 1 to 4. Yeah, this is the graph. Let's see if it works or if it gives some error. Q dot insert root. What I'm doing? Okay, insert. There is a difference in insert. Yeah, it is traversing 0, 1, 2, 3, 4. That's good. I hope you understood it. Just in case you are figuring it out, just let me know. Otherwise, we will be quickly finishing the DFS part 2. No, it's not necessary to mark the here. To see, yeah, I think that will be a better approach. So that it since it is a tree, but if it is a graph, it's better approach to mark it visited here only. Yeah, you're correct. Because in this case, it's not affecting, but in the tree, some node might get added twice. Yeah, you're correct. Good. Yeah, if the number, if they are disconnected, if there are many components, then we need to BFS from each component. Like there is one component like this, you will be taking, you will be running it from here, and it will cover all the elements that are connected to it. Then for the next connected component, we have to take such element. So suppose if you have an element, just run the for loop, and for all the element it works. I guess like if you can make a condition, if some node is not visited, run a BFS from there. So it will cover all the elements that are connected to it. Then again for loop for all the elements. Like so it will go to the next element and check if that element is visited or not. If that is not visited, again run the BFS from there. So it's like in the end, it's like whatever number of connected component is there, and the end all will be visited. No, here I haven't updated, but I'm saying that's a better approach. The things that you are saying now, that's a better. Like if you will do this now, here you have to mark visited to visited root is equal to one since we have visited the root, right? And it's good. Let's see it will work to work. I'm saying the things that you are saying is better. It is more generalized. In this case, it was working that if it is there, no? So that's why. Let's move quickly to the DFS part. Okay. The DFS part will be exactly same. We will be having a root, we will be having a data structure that essentially can visit it. This will be different. This only. Okay, in the DFS, what we were doing, if we get at some node, let it be the node. Root will confuse you. So if we get at some node, we were adding this into our answer. So let's push it back. Push back node into the answer, right? We will since we are at this node, we'll be marking this node as visited. Visited is equal to one. Now from this node, we need to check whether this node have any children or not. So for that, we will remove this of this node. If it has children, okay, if it has children, if that children is visited or not. If that is not visited, if that is not visited, we will move to that child. Okay, this child we will moving. We are calling this function again with that child being the node. Okay, days 18 and visited. That's it. Code is done. Code is get easy. I hope it will. Okay, it's giving some error. Okay, here calling BFS. We have called it. Yeah, let's see. Yeah, it's working. It's giving the correct output. Let's see if it is giving correct output now. The my input is corresponding to this one. This is not one. This is was two. This was three, and this was four. So output is 01342. 013. It at first it came to zero, like this was zero. 0 to 1, then 3, then it came here, then it see if there is child, yeah, there was child, so it came to 4, and then it goes back to 0, and then it came to 2, yeah, it's correct. So that's it. This is a code for DFS. So this is what it was written here. You can go through it. The problem is the same, like to find the shortest path is like this. You can just do it on your own. It's a bit, it's a quite simple. You can just do it. Just if you haven't done, or if you can't able to do this, just Google it. You will know the logic. but try to do it on your own. Okay, you will get this PPT. Okay, don't worry. Defense traversal. This is what we have done right now. So I guess if anybody of you have any doubt, just let me know. Otherwise, we will be wrapping up the session. One more thing is that there is an campus ambassador. Like in the attendance form, there will be a thing like campus ambassador internship. You can go through that. Like that is if there would be any DevTown boot camp or something, this kind of session in your college, you will be there. You can attend those. You can lead. You can lead there as a being the campus ambassador program for DevTown. I guess it's clear about internship too. It was like, again, I'm repeating, if there would be anything getting organized by DevTown in your college, you will be there as a campus ambassador. You will be leading. You will be getting everything there. You will have access of everything. You will know everything, and it's a kind of internship too. So it will add in your resume. When so, just fill it out if you are interested or not. Yeah. Okay. I guess things are clear to you. If something is still there, just let me know. This is our last session. So yeah, so let's wait for 1 more minute before wrapping it up. If you want to ask me something, just let me know. See, DSA for placement, I can just overview since I've given interviews and test of almost all like 150 companies, including my internship and placement too. So I can tell you one thing that just do practice, practice, and practice, and that's it. I solve around 1,000 plus code forces problem like everywhere. Just do wherever you are getting the problem. Just like it's not like solving a single kind of problem. Just go on variety. Just don't Google it if you are not understanding anything. Just try to write in your notebook what you are given, what are all the possibilities. That's what I learned. I was doing like from the first semester or second semester only. So it's take time. Don't worry if you can't solve any problem. Don't worry, like try for a problem. If you aren't getting, just leave that for that time, or try it again after some time. But if still, if you're feeling stuck, if you think the time are wasting, just Google it the approach, and then think why where until you able to solve that problem. Okay, so this is how you will learn, and try to like whatever mistake you have done before, try to recognize it too, like keep in mind too, so that you won't be doing it in the real time uh, contest or whatever. And you know that the online assessment of companies are like time based, so it's better to know the TSA and go to the contest, give contest on code sources, code self, or wherever you are comfortable, lead code, just give it. Because in the time pressurized environment, it affects a lot. If you don't have a practice in don't have practice to perform in pressurized environment, you will be just like you won't be able to do good as you should or you are capable of. Okay, so I will be suggesting, yeah. So still, if you have any doubt, just let me know. Otherwise, we will be wrapping up the session. If you need any help, you can just be connected with me on the LinkedIn. I will help you there, or just be with the DevTown. You can ask. Like there will be many mentors, so they will be helping you. Yeah, definitely. Next time we can do bootcamp like on tough topic, BP. We can go trees. These are the very basic, just the basic one. So, but definitely, if you have understood the basic, then only you can go to the top of the ladder, right? So, don't like one thing I can suggest you is that don't mug up the concept. Just know by heart everything. That's what. Like practice, just do hard work. That's it. There isn't any shortcut. I don't have. I can't say anything right now for immediate or intermediate or advanced level in future, but definitely if there would be if students wants, they can arrange. I don't have any idea right now. I can't say anything, but definitely if you all want, you can they can arrange. Okay then. Bye bye. Good night. Have a good day.